What if you could step into a machine today and find yourself standing in the middle of ancient Rome tomorrow, or take a single wrong turn and end up rewriting the future in ways you never imagined? Time travel isn't just the stuff of science fiction. It's one of the most tantalizing mysteries of our universe, a puzzle that has captivated scientists, storytellers, and dreamers for centuries. Think about the twist in your favorite time travel movie, the moment the hero realizes they've altered something small, only to watch the entire timeline unravel. That thrill, that spine-tingling "what if?" is just a glimpse into the real theories that physicists and philosophers wrestle with every day. From the grandfather paradox to the mind-bending idea of parallel universes, the possibilities are as endless as they are bewildering. Imagine a world where every decision you make splits reality into infinite versions of itself, where somewhere out there, another you took that job offer, missed that flight, or never even clicked on this video. These aren't just wild guesses, they're serious theories backed by some of the brightest minds in history, each one peeling back another layer of time's greatest secrets. And the deeper you go, the more questions arise. Could time travel already be happening without us knowing? Are there hidden cracks in the fabric of reality where the past and future bleed together? That's exactly what we're diving into today, 30 of the most astonishing, thought-provoking theories about time travel that will make you question everything you thought you knew. Whether it's Einstein's groundbreaking ideas about warped spacetime or the eerie concept of closed time-like curves that could let you meet your past self, we're about to explore the edges of what science dares to imagine. So buckle up, because by the end of this journey, you might never look at a clock the same way again. One of the strangest ideas in time travel isn't about changing history, it's about erasing origins altogether. Picture this: you're a struggling musician in the future when a stranger hands you a notebook filled with song lyrics that become your greatest hits. Years later, you travel back in time and give those same lyrics to your younger self, the very person who once gave them to you. Where did the songs actually come from? This is the Bootstrap paradox, a dizzying loop where cause and effect tie themselves in knots, leaving behind a mystery with no clear beginning. The name comes from the phrase, pulling yourself up by your bootstraps, an impossible task, just like trying to trace the origin of something caught in this cycle. Take a famous example from science fiction. A physicist receives a blueprint from their future self, builds a time machine using those plans, and then travels back to deliver the same blueprints to their past self. The design exists, but no one ever created it. It's a cosmic glitch where the object or information has no original creator. It simply exists because it always has. What makes this paradox so unsettling is how it defies our basic understanding of reality. We're wired to think in straight lines. Every effect has a cause, every invention has an inventor. But the Bootstrap paradox throws that out the window. Imagine finding Beethoven's Lost Symphony in a time capsule, painstakingly copying it note for note, and then sending it back to the 18th century where it's discovered by Beethoven himself. The music exists, but its true source vanishes like smoke. Some scientists argue this could actually happen in a universe where time travel is possible. If closed time-like curves, those theoretical pathways through warped spacetime exist, information or objects could loop endlessly without an origin point. It's a concept that blurs the line between creation and discovery, leaving us to wonder, are some ideas just eternal, floating outside of time, waiting to be found, or perhaps waiting to be returned? Now let's talk about a scenario so unsettling it keeps physicists up at night: the grandfather paradox. Imagine traveling back in time and accidentally or intentionally killing your own grandfather before he meets your grandmother. Without their union, your parent would never be born, which means you would never exist. But if you don't exist, how did you travel back to commit the act in the first place? This is the ultimate self-canceling loop, a logical nightmare that seems to make time travel impossible unless reality has a workaround. One way out of this paradox comes from the idea of parallel universes, also known as the multiverse theory. Instead of altering your own past, your actions might simply branch off into a new timeline. In this version of events, killing your grandfather wouldn't erase you. It would just create a separate reality where you were never born, while the original timeline, the one you came from, continues untouched. You'd be like a ghost in the machine, existing outside the consequences of your own actions. But what if the universe is more stubborn than that? Some theories suggest reality has a built-in resistance to paradoxes, bending and twisting to ensure consistency. In this view, time might act like a self-healing wound. No matter how hard you try to change the past, something would always stop you. Maybe your gun jams at the crucial moment, or a sudden noise distracts you. The universe, in this case, becomes an active participant, enforcing the rules like a cosmic referee. Then there's the notion of predestination, where your attempts to alter history were always part of the timeline. What if your grandfather survived the encounter because you were never really a threat? Or worse, what if your actions set in motion the exact chain of events that leads to your own birth? That's the cruel irony of time travel. You might think you're breaking free of fate, only to realize you are playing your assigned role all along. Scientists and philosophers have wrestled with these ideas for decades, testing them against the laws of physics and logic. Quantum mechanics even hints at possibilities where particles can exist in multiple states at once. So why not entire timelines, whether through parallel worlds, cosmic censorship, or eerie loops of inevitability? The grandfather paradox forces us to confront one stark truth: time isn't just a river we can swim against. It might be an ocean with currents and whirlpools we're only beginning to understand. While the grandfather paradox paints time travel as a dangerous game of cosmic undo buttons, there's a theory that flips the script entirely, suggesting the universe might be far more rigid than we think. Enter the Novikov self-consistency principle, a bold idea from Russian physicist Igor Novikov that claims paradoxes can't exist because any actions taken by a time traveler were always part of history. Think of it like this: every move you make in the past was already baked into the timeline, leaving no room for contradictions. It's not that you can't change the past, it's that you already didn't. Take one of history's most infamous figures, Adolf Hitler. Countless stories imagine assassinating him before his rise to power, but Novikov's principle suggests such attempts would inevitably fail. Maybe the gun misfires or a sudden distraction intervenes, not by chance, but because history requires Hitler to survive long enough to set later events in motion. The universe, in this view, operates like a meticulously edited film. Every scene, including your time-traveling interference, fits together without loose ends. This idea gets even wilder when applied to everyday scenarios. Imagine traveling back to give Shakespeare a copy of his own plays. Under Novikov's rule, those pages couldn't contain anything new. They'd just be duplicates of works he'd already written, because altering his creative process would create a paradox. The principle turns time into a closed loop where cause and effect are locked in sync, like gears in a machine that can't slip. But how could the universe enforce such consistency? Some physicists speculate that quantum mechanics might play a role, with tiny probabilities conspiring to keep events on track. If you tried to disrupt a pivotal moment, countless unseen factors, a gust of wind, a misplaced thought, could steer you away without you even realizing it. It's as if time has an immune system, attacking inconsistencies before they can spread. Of course, this raises eerie questions about free will. If your actions in the past were predetermined, does that mean your future is fixed too? Novikov's principle doesn't necessarily doom us to fate. It just suggests that time travelers, like all historical actors, were always part of the tapestry. Whether that's comforting or claustrophobic depends on how you view the threads of your own life. What makes this theory so compelling is its simplicity. Unlike multiverses or cosmic censorship, it doesn't require invisible timelines or reality police, just a universe that refuses to contradict itself. And while we can't yet test it, the very possibility reshapes how we imagine time travel, not as a tool for rewriting history, but as a way to rediscover how deeply entangled every moment truly is. What if every choice you make doesn't just change your future? It creates an entirely new universe. This isn't science fiction. It's the heart of the many worlds interpretation, one of quantum mechanics' most mind-bending ideas. Picture standing at a crossroads. One path leads left, the other right. In our everyday experience, you'd pick one and move on. But according to this theory, the universe splits at that moment. One version of you goes left, another goes right, and both realities unfold simultaneously, utterly unaware of each other. Now, imagine time travel in a world where every decision branches into infinity. Suddenly, the grandfather paradox isn't a problem. It's just another fork in an endless road of possibilities. The many worlds interpretation was first proposed by physicist Hugh Everett in the 1950s as a way to explain the bizarre behavior of particles at the quantum level. At that tiny scale, particles exist in multiple states at once, a concept called superposition, until they're observed, collapsing into a single outcome. Everett's radical suggestion: those other outcomes don't vanish, they play out in parallel universes. Every quantum event, from the decay of an atom to the firing of a neuron in your brain, spawns new realities. It's like a cosmic game of choose your own adventure, except every possible choice is taken. For time travelers, this changes everything. Instead of worrying about erasing your own existence by altering the past, you'd simply hop onto a new timeline. Step on a butterfly in the Jurassic era. That atrocity plays out in one universe while the original timeline, your home, remains untouched. The many worlds interpretation turns time travel into a form of dimensional tourism, where consequences are confined to the reality you're visiting. No paradoxes, no universe-fixing mechanisms, just an infinite tapestry of worlds, each with its own version of history. But here's where it gets even stranger. If every possible outcome exists somewhere, then there's a universe where you never traveled back at all, one where you arrived a minute earlier, and even one where dinosaurs evolved into the dominant intelligent species. The implications are staggering. Lost a loved one, there's a world where they're still alive. Regret a decision, another version of you is living the life you wish you'd chosen. This isn't just about alternate histories, it's about alternate yous, each shaped by different choices, different chances. Critics argue that the many worlds interpretation is untestable after all. We can't observe these other realities. But supporters counter that it's the most elegant solution to quantum weirdness, removing the need for mysterious collapse events when particles are observed. And for time travel, it offers something priceless: freedom. Freedom to explore, to interact, even to make mistakes without the fear of unraveling existence itself. Of course, with freedom comes existential weight. If every possibility is realized somewhere, does anything truly matter? Is the you reading this just one thread in an unfathomably vast cosmic quilt? The many worlds interpretation doesn't just reshape how we think about time travel, it challenges our very sense of self. Maybe that's the most thrilling part, the idea that somewhere in some other universe, another version of you is pondering these same questions and reaching entirely different conclusions. Einstein's theory of relativity didn't just redefine gravity, it ripped open the possibility of time loops hidden in the fabric of spacetime itself. These strange pathways, known as closed timelike curves, are like cosmic Möbius strips where the future bends back to meet the past, allowing time travel without breaking the universe's speed limit. Think of spacetime as a vast stretchy sheet, warped by massive objects like stars and black holes. Normally, time flows in one direction like a river. But under extreme conditions, say, near a spinning black hole or an infinitely long cosmic string, that sheet could twist so tightly it forms a tunnel where the end connects to the beginning. Step inside and you might find yourself walking out into your own past. The math behind this is startlingly elegant. Einstein's equations describe gravity not as a force, but as curves in space-time created by mass and energy. Solve those equations under specific conditions, like the intense rotation of a Kerr black hole, and you get solutions where time folds into a loop. Unlike science fiction's flashy time machines, CTCs don't require exotic engines or warp drives. They're more like natural fault lines in reality, where the usual rules of cause and effect take a backseat. One hypothetical example: a spaceship orbiting a rapidly spinning black hole at just the right angle could complete a journey that returns it to its own launch date. The crew wouldn't feel anything unusual, just the steady pull of gravity. Yet they'd emerge hours, days, or even years before they left. But here's the catch: these loops aren't free passes to rewrite history. Many physicists argue that CTCs would enforce Novikov's self-consistency principle, meaning any actions taken inside the loop were always part of the timeline. Try to leave yourself a warning note in the past, and you might find the paper crumpled in your pocket, the universe correcting itself to avoid paradoxes. Others suggest quantum mechanics could allow multiple outcomes within the loop, with probabilities balancing out to keep reality intact. It's as if space-time has a built-in editing room, trimming inconsistencies before they hit the final cut. The implications are dizzying. If CTCs exist, events might not have single, linear causes. An ancient artifact could appear in a museum with no creator, its existence explained by a time traveler who found it there centuries later. Historical records might echo with unexplainable repetitions, like déjà vu on a cosmic scale. Even our sense of free will comes into question. If your future actions are already written into the past, are you really choosing anything? Yet for all their theoretical elegance, closed time-like curves remain controversial. Some scientists argue they're mathematical artifacts, vanishing under more complete physics. Others see them as clues to a deeper truth, that time isn't the rigid arrow we perceive, but a flexible dimension where past, present, and future are woven together in ways we're only beginning to glimpse. Whether they're cosmic shortcuts or mere mirages, CTCs remind us that the universe's rulebook might be far stranger than we ever imagined. What if you could build a time machine not with flashing lights or mysterious portals, but with something as simple as a spinning column of metal? That's the audacious idea behind Tipler's cylinder, a hypothetical cosmic structure dreamed up by physicist Frank Tipler in the 1970s. Imagine a cylinder so dense and massive, think neutron star material, rotating at nearly the speed of light. According to Einstein's equations, this whirligig of condensed matter wouldn't just bend spacetime slightly, it would twist it like a corkscrew, creating a closed time-like curve around its surface. Walk a careful path along its exterior, and you might find yourself returning to your starting point, not just in space, but in time. But here's the catch: this cosmic time machine comes with specs that push the limits of reality. For the cylinder to work, it would need to be infinitely long, not just astronomically large, mathematically endless. Why? Because a finite cylinder would create gravitational turbulence at its ends, disrupting the delicate spacetime loop needed for time travel. Picture trying to roll a sheet of paper into a perfect ring. It curls neatly until you reach the edges where it frays. Tipler's solution: remove the edges entirely. The cylinder can't have ends, or the whole delicate warp collapses. Then there's the small matter of materials. The cylinder would need a density beyond anything we've observed, packing the mass of multiple suns into a structure just a few kilometers wide. Neutron stars, the densest known objects in the universe, come close, but even their immense gravity isn't enough. Some calculations suggest you'd need exotic matter with negative energy to stabilize the cylinder, a substance that defies known physics. It's like trying to build a bridge out of shadows, theoretical but nowhere near practical. Yet for all its absurd requirements, Tipler's thought experiment isn't just a flight of fancy. It reveals something profound about the relationship between gravity, rotation, and time. Black holes warp space-time so severely that light can't escape, but a spinning cylinder could twist it into a new kind of knot, one where time itself spirals back on itself. The idea also hints at a tantalizing possibility. Maybe time travel doesn't require understanding entirely new physics. Maybe we just need to stretch Einstein's relativity to its breaking point. Of course, the infinite length problem isn't just an engineering headache, it's a philosophical one. In a finite universe, how could anything truly infinite exist? Some theorists have proposed workarounds, like arranging multiple cylinders in precise formations to mimic infinity. But these solutions feel like stacking one improbability onto another. And even if we could build it, the cylinder's time loops would only allow travel to moments after its creation. Want to visit the dinosaurs? Too bad. Tipler's cylinder is less a DeLorean and more a fixed-track roller coaster, looping through a sliver of time you'd be stuck riding forever. What makes this concept so compelling isn't its practicality, it's the way it forces us to confront the raw power of gravity and motion. A spinning column shouldn't be able to rewrite history, yet the math insists it's possible. That tension between the mundane and the miraculous is what makes time travel theories so irresistible. They take the familiar rules of reality and twist them until the impossible starts to look inevitable. So while we may never see a Tipler cylinder looming in space, its legacy endures as proof that even the simplest motions, spin, stretch, repeat, might hold the keys to the universe's greatest mysteries. Wormholes aren't just shortcuts through space, they could be bridges between eras, tunnels where the walls are made of time itself. Picture a cosmic subway system. Step in one end and emerge light years away or centuries in the past. The concept comes straight from Einstein's equations, which describe space-time as a flexible fabric that can fold, pinch, or even tear under extreme conditions. A wormhole is essentially two black holes connected by a throat, a passage where the usual rules of distance and duration don't apply. But here's the twist. If you could drag one end of the wormhole near a black hole or accelerate it to near light speeds, time dilation would kick in. While minutes pass for the stationary end, years could fly by for the moving one, creating a time difference ripe for exploitation. The real challenge isn't just finding a wormhole, it's keeping it open long enough to use. Nature hates unstable shortcuts. Most theoretical wormholes snap shut instantly under their own gravity, crushing anything inside like a cosmic bear trap. To prevent this, you'd need something called exotic matter, a hypothetical substance with negative energy density. Unlike normal matter, which attracts via gravity, exotic matter would repel, propping open the wormhole's throat like scaffolding in a tunnel. The catch: we've never observed exotic matter in the wild. It exists as a quirk in quantum field theory, where tiny amounts of negative energy might flicker into existence at microscopic scales, far too little to stabilize a traversable wormhole. Even if we solved the exotic matter problem, there's the issue of navigation. Wormholes aren't leisurely strolls, they're chaotic environments where gravity gradients could stretch you into spaghetti or fry you with intense radiation. Some models suggest lining the throat with ultra-smooth materials to minimize tidal forces, while others propose using electromagnetic fields as shields. But the most unsettling possibility: wormholes might already exist, remnants of the early universe's violent expansion, lurking unseen until someone or something figures out how to unlock them. Perhaps the strangest implication of wormhole time travel is its bootstrap potential. Send a message through a wormhole to your past self, and you create information with no origin, a paradox wrapped in an enigma. Yet some physicists argue this might be a feature, not a bug. If the universe permits wormholes, it might also enforce self-consistent loops where effects precede causes without collapsing reality. Imagine finding a dusty textbook in your attic, filled with equations for wormhole stabilization, only to realize decades later you're the one who must send it back in time to close the loop. What makes wormholes so tantalizing is their duality. They're both a mathematical certainty and a practical nightmare. They tease us with the promise of bending time while demanding technologies we can barely conceive of. Yet they remind us that space-time isn't the rigid stage we perceive. It's a dynamic, malleable thing, full of hidden doorways waiting to be discovered. Whether they're nature's glitches or artifacts of a deeper physics, wormholes challenge us to rethink not just how we travel through time, but how time itself is woven into the universe's fabric. The fastest way to visit the future might not involve flashy machines or cosmic tunnels, just raw speed and gravity's unforgiving grip. This is time dilation, relativity's gift to would-be time travelers, where the universe itself conspires to warp the flow of time based on motion and mass. Picture identical twins. One stays on Earth while the other blasts off in a spaceship nearing the speed of light. When the traveling twin returns after what feels like a few years, Earth might have aged decades. Their reunion isn't just emotional, it's a collision of two different timelines, proof that time isn't a universal metronome but a fluid rhythm shaped by speed and gravity. Einstein's special relativity reveals this startling truth. The faster you move through space, the slower you move through time. At everyday speeds, the effect is negligible. Your commute to work doesn't noticeably age you slower than your neighbor. But crank your velocity up to 99% of light speed, and time for you dilates dramatically. A 2-year journey at that pace could mean 50 years back home. It's not science fiction. We've measured this with atomic clocks on fast-moving jets, though the difference was mere nanoseconds. Scale it up, and the implications are staggering. A crewed mission to a nearby star system at relativistic speeds could return to an Earth where their great-grandchildren are older than they are. Gravity bends time just as fiercely. General relativity tells us that clocks tick slower in stronger gravitational fields, meaning time crawls near a black hole's event horizon compared to interstellar space. Park a ship just outside the point of no return, and hours on board could equal years for distant observers. This isn't theoretical. GPS satellites orbiting Earth must account for tiny time differences caused by our planet's gravity, or their navigation data would drift by kilometers. Near a supermassive black hole, the effect becomes extreme. In the movie Interstellar, the crew's hours on the water planet cost them 23 Earth years, a poetic but scientifically plausible exaggeration. What makes relativistic time travel so compelling is its inevitability. Unlike wormholes or Tipler cylinders, which demand hypothetical physics, time dilation is already woven into the universe's operating system. We don't need to invent warp drives to exploit it. Just overcome the monstrous energy requirements of near-light-speed travel. Even then, there's a cruel limitation. This method only sends you forward. There's no returning to your original era, no rewriting history. You're a temporal castaway, forever stranded in the future you raced toward. Yet for all its one-way nature, time dilation offers something profound, proof that the future is malleable. Not through paradoxes or alternate timelines, but through the simple, brutal mechanics of motion and gravity. Every time you sprint for a bus or ride an elevator, you're technically time traveling, just on a scale too small to notice. The universe is constantly whispering its secrets. We're only now learning to listen. So while we might never build a machine that spins backward through centuries, the stars themselves hold a roadmap to the future written in the warped fabric of space-time. Some of the cruelest twists in time travel aren't about changing history, they're about realizing you were always part of it. This is the predestination paradox, a mind-bending scenario where every attempt to alter the past only locks events more firmly into place. Think of it as cosmic irony on steroids. You travel back to stop a disaster, only to discover your actions set the disaster in motion. The classic film 12 Monkeys plays this beautifully. The protagonist's frantic efforts to uncover the source of a deadly plague end up spreading the very pathogen he hoped to contain. The harder he fights against fate, the tighter its grip becomes. This paradox gets its teeth from a simple but chilling truth. Free will might be an illusion in a universe with time travel. Take the haunting tale of John Connor in Terminator. Kyle Reese is sent to protect Sarah Connor from a killer android, fathers John with her, and dies only for John to grow up and send Reese back in the first place. The loop is sealed. No Reese, no John, no John, no Reese. There's no original starting point, just an endless cycle where cause and effect chase each other like snakes eating their own tails. What makes these loops so unsettling is how they weaponize good intentions. Imagine traveling to prevent your parents' car accident, only to cause the swerve that sends them off the road. Or warning a scientist about the dangers of their invention, inadvertently giving them the final clue to perfect it. History isn't just resistant to change, it's predatory, turning your resistance into its fuel. Some philosophers argue this suggests a deterministic universe, where every event is pre-scripted and time travelers are merely actors reading lines they can't see. But there's a flip side to this nightmare. If predestination loops are real, they might explain eerie historical coincidences like the Titanic's ignored warnings or Hindenburg's doomed flight. Maybe someone did try to stop these tragedies, only to become the reason they happened. The paradox turns history into a locked room mystery where every clue points back to the detective. Quantum physics offers a potential escape hatch. If particles can exist in multiple states until observed, perhaps time travelers create branching realities where some versions of events unfold unchanged while others spiral into new timelines. But in a pure predestination model, there are no branches, just a single, inescapable thread. You're not fighting time, you're dancing to its rhythm, mistaking your steps for rebellion. The genius of this paradox is how it reframes time travel from a tool into a trap. It's not about what you can change, it's about realizing you already did and always will. Every warning, every intervention, every desperate leap was just another stitch in the tapestry. That's the true horror of predestination. The moment you recognize the universe has been playing chess while you thought you were playing solitaire. Quantum entanglement already feels like magic. Two particles linked across vast distances, instantly mirroring each other's states no matter how far apart they are. But what if this spooky connection doesn't just bridge space but time? Some physicists speculate that entangled particles could be whispering secrets backward through the ages, turning causality on its head in ways that make time travel seem almost mundane. Imagine flipping a coin in your lab today and its entangled twin, sitting in a lab 100 years ago, instantly lands on the same result, the present influencing the past. It's not just possible, the math might already allow it. This wild idea stems from a phenomenon called retrocausality, where effects precede their causes. In the quantum realm, particles don't play by classical rules. Experiments like the delayed choice quantum eraser suggest that a particle's behavior can be influenced by decisions made after it's been measured, as if the future reaches back to tweak the past. It's like mailing a letter and then, days later, choosing whether it was sent express or standard, somehow altering how fast it traveled in retrospect. If entanglement can stretch across time as well as space, it could create a loophole where information slips backward, bypassing the usual one-way flow of cause and effect. Critics argue this breaks relativity's speed limit. Nothing, not even information, should outpace light. But proponents counter that retrocausality doesn't require faster than light signals. Instead, it's more like a cosmic handshake where cause and effect are negotiated in advance, locked in a loop that only makes sense when viewed from outside time. Think of it like a detective solving a crime where the murder weapon is found before the killer pulls the trigger. The The sequence is scrambled, but the outcome stays consistent. The implications are staggering. If quantum systems can encode future events into past states, time itself might be more like a tapestry than an arrow woven with threads that cross and double back. This could explain why quantum particles seem to know outcomes before they're measured, as if their probabilities are shaped by events yet to come. Some interpretations even suggest that observers in the present might be enacting a kind of temporal diplomacy, unconsciously negotiating with past versions of reality to settle on a mutually consistent timeline. Of course, this isn't a free pass for paradoxes. Any backward-in-time influence would likely be self-correcting, ensuring no grandparent gets erased and no universe-ending contradictions arise. The universe might allow tiny time loops at the quantum scale, where information circulates like water in a sealed fountain, never overflowing, never draining, just perpetually in motion. What makes this theory so tantalizing is its humility. Unlike wormholes or warp drives, it doesn't demand engineering on galactic scales. The machinery for time-bending communication might already exist, hidden in the spine-tingling behavior of particles we're only beginning to understand. Whether retrocausality holds up under scrutiny or collapses like a quantum probability wave, it forces us to confront a radical idea. The future might not just be written in the stars, it could be scribbling notes in the margins of the past. A single misplaced footstep in the Jurassic era could ripple outward like a shockwave, rewriting millions of years of evolution in ways no time traveler could predict. This is the butterfly effect chaos theory's haunting reminder that even the tiniest disturbance can cascade into catastrophic consequences. The name comes from meteorologist Edward Lorenz, who discovered in the 1960s that rounding a number in a weather model by less than 1% could transform a forecasted sunny day into a simulated hurricane weeks later. His revelation, reality is hypersensitive. Flap a butterfly's wings in Brazil today, and you might ignite a typhoon halfway around the world next month. Now apply that instability to time travel, where every interaction, a moved pebble, a whispered word, could snowball into a future unrecognizable to the traveler who touched it. Some physicists argue time might have a built-in immune system against such chaos. The idea of self-healing timelines suggests that small changes could be absorbed or corrected by the universe's natural turbulence. Think of dropping a stone into a rushing river. The initial splash disturbs the surface, but the current quickly smooths it away. Similarly, minor alterations might get drowned out by history's momentum. Miss your train in 1920. The stranger who would have sat beside you simply chats with someone else, their descendants still meeting, marrying, and birthing the same people who shaped the future. The larger patterns hold firm because human behavior, weather systems, and even quantum fluctuations have countless pathways to reach similar outcomes. But not all changes are equal. Certain moments, temporal tipping points, might be so fragile that the slightest nudge sends history careening. Prevent a single quarrel between Hitler's parents, and the 20th century veers onto an unrecognizable path. Save a doomed inventor, and technology leaps forward decades ahead of schedule. Scientists speculate these critical junctures exist where systems are metastable, balanced so precariously that a feather's touch can topple them. The rest of time, like a ball in a valley, push it and it rolls back to equilibrium. The terrifying beauty of the butterfly effect is that it turns time travel from a tool into a game of Russian roulette. You might return to a future where your hometown never existed, or find everything eerily unchanged, your interference lost in the noise of history's currents. Either way, one truth remains: tampering with time isn't about steering the river. It's about discovering whether you're throwing a pebble or dynamite into its depths. What if every move you make in the past isn't changing history, but completing it? The immutable timeline theory flips the script on traditional time travel narratives by suggesting that the past is unshakable, and any attempt to alter it only ensures it happens exactly as recorded. Take Harry Potter and the Prisoner of Azkaban, where Harry's desperate efforts to save his past self from Dementors inadvertently reveal that his salvation always came from his own future actions. There was no alternate version of events, just a single, unbroken thread where his time-traveling intervention was always part of the story. This isn't just clever storytelling, it's a real philosophical stance on how time might actually work. The theory hinges on the idea that the universe enforces consistency. If you travel to the past, your presence and actions were already factored into history, like a jigsaw piece snapping into a predetermined slot. Imagine discovering an ancient cave painting that perfectly depicts your time machine. Under the immutable timeline model, that artwork wasn't a prophecy, it was always a record of your eventual arrival. The past doesn't bend to new events, it absorbs them seamlessly, leaving no room for paradoxes or contradictions. Even your attempts to defy fate would be the very mechanisms that fulfill it. This perspective resolves some of time travel's thorniest problems. No grandfather paradoxes, no butterfly effects, just a cosmic script where every traveler plays their assigned role. But it also raises unsettling questions about free will. If your future actions are already etched into the past, are you really making choices or just acting out a story written long before you arrived? Some philosophers argue that this doesn't eliminate free will but redefines it. Your decisions still matter because they're the ones that created the timeline in the first place. You're not a puppet, you're the author, retroactively signing your name on events that were always yours to shape. Historical mysteries might hold clues to this phenomenon. Consider the eerie case of the Tunguska event, a massive explosion over Siberia in 1908. Some conspiracy theorists suggest it was caused by a time traveler trying to prevent a future catastrophe, only for their interference to become the very disaster they sought to avert. Under the immutable timeline theory, that's not a glitch, it's the universe operating as designed. Even our most defiant acts might be threads in a tapestry woven long before we took our first step. The beauty of this model is its elegance. Unlike multiverses or self-correcting timelines, it doesn't require branching realities or cosmic editing. There's just one history, infinitely resilient, integrating every temporal intervention like echoes in a canyon. For would-be time travelers, it's a humbling thought. You can't rewrite the story. You can only discover too late that you are always part of the ink. What if every moment in history isn't lost to time but etched into the fabric of the universe like grooves on a cosmic record? The holographic principle, a radical idea born from black hole physics, suggests that all the information defining our three-dimensional reality might actually be encoded on a two-dimensional boundary at the edge of the cosmos. Think of it like a movie projected from a flat screen. What we experience as depth, movement, and even the flow of time could just be an illusion, shadows dancing on the walls of a much stranger reality. And if that's true, then the past and future might not be gone or unformed. They could be frozen in the universe's ultimate storage device, waiting to be played in the right sequence. This theory starts with black holes, those space-time warping monsters whose event horizons trap information forever, or so we thought. In the 1970s, physicist Jacob Bekenstein calculated that the entropy of a black hole, its hidden information, was proportional to its surface area, not its volume. Decades later, Leonard Susskind and Gerard T. Hooft took this further, proposing that all the particles, forces, and events inside a region of space could theoretically be described by data written on its outer surface. It's like compressing every scene from the Lord of the Rings trilogy onto a DVD. The richness isn't lost, just translated into a more compact format. Now, stretch this idea to the entire universe. If our 3D reality is a projection from a 2D boundary, time might not flow the way we perceive it. Instead of a river moving from past to future, every moment could exist simultaneously, layered like frames on a film reel. Want to revisit ancient Egypt? Under this model, the information encoding Pharaoh Ramses' reign isn't gone. It's still out there on the cosmic hard drive preserved at the edge of space-time. Time travel wouldn't require bending the universe's rules. It'd just mean accessing the right file in the holographic archive. But here's where it gets truly bizarre. If the past, present, and future are all equally real, just different slices of the same hologram, then free will starts to look like an illusion. Your choices might feel real, but they could be predetermined by the hologram's code, playing out like scenes in a movie already burned onto the disk. Some physicists counter that this doesn't eliminate agency. It just means our decisions are part of a higher dimensional pattern we can't yet perceive. Either way, the holographic principle blurs the line between memory and prophecy, suggesting that what we call time might just be the order in which the universe reads its own data. The most tantalizing implication: this could solve time travel's biggest headache, paradoxes. In a holographic universe, changing the past wouldn't create contradictions. It'd just rewrite the code on the boundary, updating the projection seamlessly. No grandfather paradox, no butterfly effect. Your actions in ancient Rome would simply become part of the hologram's new rendering, like editing a video file without breaking the playback. Of course, skeptics point out we've found no direct evidence of this universal hologram. Yet the math holds up eerily well, and experiments with quantum gravity hints at pixelated spacetime at tiny scales, like glimpsing the pixels of the cosmic projector. Whether the holographic principle is the key to time or just a beautiful metaphor, it forces us to confront a humbling idea: the past might not be behind us. It could be all around us, written in light on the walls of reality, waiting for someone or something to hit rewind. Among all the bizarre phenomena in physics, few are as mesmerizing or as paradoxical as time crystals. These aren't gems from a sci-fi vault. They're a real, experimentally confirmed phase of matter that defies one of the universe's most sacred laws, the arrow of time. Picture a snowflake that doesn't just sit frozen in space but pulses rhythmically in time, cycling through its structure without ever losing energy. Unlike clocks or pendulums which wind down, time crystals keep ticking forever, not by consuming fuel but by exploiting quantum weirdness to create motion without decay. It's as if you invented a wheel that spins eternally without friction, or push a perpetual motion machine that doesn't break physics but bends it to its will. The secret lies in their quantum structure. Normal crystals like diamonds or salt have atoms arranged in repeating patterns in space. Time crystals add an extra dimension. Their atoms oscillate in a repeating sequence over time, flipping between configurations like a cosmic metronome. This isn't just theoretical. In 2017, researchers at Harvard and the University of Maryland created the first time crystals using chains of ytterbium atoms or nitrogen vacancies in diamonds. When zapped with lasers, these systems didn't respond immediately. Instead, they pulsed at a rhythm half the speed of the laser's frequency, a hallmark of time translation symmetry breaking, where the system's periodic motion outlasts the energy input. What makes time crystals so tantalizing for time travel isn't just their defiance of equilibrium. They're natural models for closed time-like curves, those loops in spacetime where cause and effect fold back on themselves. Think of a time crystal's endless cycle as a miniature, self-contained time loop. Its atoms don't move forward, they dance in a circle, returning to their starting point again and again. Scale this up, and you might unlock systems where information or even matter could orbit its own history, protected from entropy's erasure. Yet the most radical possibility isn't building time machines. It's that time crystals could reveal time itself as an emergent property, something that arises from quantum interactions rather than flowing independently. If time is more like a pattern than a river, then manipulating it might not require warping spacetime. You just need to reweave the pattern's threads. For now, time crystals exist in fragile, microscopic forms, light years away from powering time loops, but their existence proves something profound. even time's relentless march might have loopholes hidden in the quantum fine print. And if we ever learn to read them, the future or the past might be closer than we think. Schrödinger's cat taught us that a particle can exist in two states at once, alive and dead, until someone peers into the box and collapses the possibilities into one. But what if that same quantum weirdness didn't just apply to particles or felines, but to you? Enter the quantum suicide thought experiment, a chilling twist on the classic paradox that forces us to confront whether time travel could splinter reality into infinite versions of itself, each one hinging on your survival or demise. Picture this: you're a time traveler with a gun rigged to a quantum trigger. Every time you pull it, there's a 50% chance the weapon fires. In one reality, the gun goes off and your story ends, but in another, the trigger fails and you walk away unharmed. Now imagine repeating this experiment over and over. From your perspective, you'd only ever experience the realities where the gun jams, because in the ones where it fires, you're no longer around to observe the outcome. It's like playing Russian roulette with the universe itself, where every click of the hammer splits the timeline, leaving you forever teetering on the edge of existence. This eerie scenario, first proposed by physicist Max Tegmark, isn't just about mortality, it's a window into how time travel might intersect with quantum mechanics. Each decision a traveler makes could spawn branching realities, with consciousness sliding seamlessly into the paths where survival is guaranteed. Think of it as the ultimate selection bias. You'd never notice the timelines where your journey ended abruptly, because your awareness is tethered to the versions where you persist. The implications are staggering. If this holds true, then every time traveler who ventures into the past might unknowingly spin off countless doomed realities, worlds where their actions led to catastrophe or where they simply vanished, while their own consciousness glides forward along the one thread where they succeeded. Some interpretations take this further, suggesting quantum suicide could be a form of accidental immortality. A traveler leaping into a black hole might, from an outside perspective, be torn apart by tidal forces. But from their viewpoint, they'd only experience the vanishingly rare quantum fluctuations where every atom in their body tunnels to safety, emerging unscathed on the other side. It's a cosmic game of chance where the traveler, against all odds, always rolls the winning number, because the alternative outcomes are erased from their perception the moment they occur. Critics argue this leans too heavily on the controversial many worlds interpretation of quantum mechanics, where every possibility spawns a parallel universe. But supporters counter that it's a natural extension of the math. If reality splits at every quantum decision, then time travel doesn't just branch history, it forces the traveler's consciousness to surf the wave of probabilities, forever riding the crest of survival. The real horror or beauty of this idea lies in its invisibility. You'd never know if you're the original version of yourself or the lone survivor of countless silent catastrophes. Every near miss, every stroke of luck might not be luck at all, but the universe pruning away the branches where your story ended too soon. So the next time you barely dodge a speeding car or recover from a fever that should have been fatal, ask yourself, how many other versions of you weren't so lucky? And if time travel is ever possible, will we even realize we're walking through a hall of mirrors, each reflection a reality where we didn't make it out alive? Ever noticed how certain memories feel almost right, like a scene from a movie with one line changed, or a brand name spelled slightly differently than you swear it was? This eerie phenomenon has a name: the Mandela Effect, where large groups of people vividly recall events or details that never actually happened. The term comes from Nelson Mandela's death, or rather, the false memories of it. Thousands insist they remember news coverage of him dying in prison in the 1980s, despite him passing away in 2013. But what if these collective false memories aren't just misfiring neurons? What if they're glitches in time itself, evidence of timeline shifts where reality has been stealthily overwritten? Take the infamous Berenstain-Bears debate. Generations of readers would bet their childhoods that the beloved book series was spelled Berenstein with an E, not Berenstain with an A. The sheer volume of people who share this exact false memory is staggering, far beyond typical forgetfulness. Some theorists suggest this isn't a mistake at all, but a relic from a previous version of reality where the name was spelled differently. In this view, time isn't a straight line. It's a branching network where edits ripple backward, leaving traces in our minds like footprints in wet cement. Then there's Star Wars fans' collective meltdown over Darth Vader's iconic line. Ask anyone and they'll recite, "Luke, I am your father," except that's not what he says. The actual line is, "No, I am your father." How could so many misquote a cultural touchstone so precisely? One wild explanation. In an alternate timeline, the line did match the misquote, but a shift in reality tweaked the scene, leaving only our memories as proof of the change. Skeptics argue these are just quirks of human cognition, our brains filling gaps with logical assumptions or blending similar-sounding words. But the consistency of these errors is unsettling. Why do so many remember the Monopoly man with a monocle when he's never had one? Or recall Curious George with a tail despite being a tailless ape? If these were random mistakes, the variations would be all over the place. Instead, the false memories cluster around specific, identical details, as if entire populations experienced the same alternate past. Could this be evidence of parallel universes bleeding into each other? Quantum physics allows for the possibility of multiple realities coexisting, and if timelines occasionally converge or overwrite one another, our memories might retain echoes of the old version. It's like waking from a dream where everything feels familiar, only to realize the world's been rearranged overnight. For time travelers, this raises a chilling question. If history can be rewritten so seamlessly that only our minds notice, how many times has it already happened without us knowing? The Mandela Effect might be the closest thing we have to a cosmic undo button, a glimpse into a multiverse where time isn't fixed and reality is far more malleable than we dare admit. So the next time someone corrects you on how you think something was, don't just shrug it off. Ask yourself, is your memory wrong or has the universe been edited? Imagine holding a tattered notebook filled with equations that just might change the world, only to realize later that you're the one who will eventually write them, inspired by the very book now in your hands. This is the ontological paradox, a dizzying loop where things or ideas exist without any clear origin, trapped in a cycle of creation with no true beginning. It's like finding an ancient artifact in a museum, studying it for years, and then traveling back in time only to leave that same artifact where it was originally discovered. The object exists, but no one ever made it. It's always just been there. Take the classic example of Shakespeare. Suppose a time traveler hands him a complete manuscript of Hamlet, which he then copies word for word and presents as his own work. Centuries later, the same manuscript is found, given to the time traveler, who then delivers it to Shakespeare. Where did the play truly come from? There's no original author, just an endless loop where the masterpiece writes itself. The paradox gets its name from ontology, the study of existence, because it forces us to ask, how can something exist if it was never created? This isn't just a thought experiment. Some scientists argue that if closed time-like curves, those twisted pathways through space-time, are possible, then information or objects could circulate endlessly without an origin point. Imagine a song that becomes famous because a musician claims to have received it from a stranger in the future. Decades later, the now older musician travels back and gives that same song to their younger self. The melody echoes through time with no composer, no first draft, no moment of inspiration, just an eternal recurrence of notes. What makes the ontological paradox so unsettling is how it upends our most basic assumptions about cause and effect. We're wired to think in straight lines. A painter dips their brush, a writer puts pen to paper, an inventor sketches a blueprint, but in these loops, creation becomes a mirage. The Bootstrap Paradox, where an object or piece of information is its own cause, is a close cousin, but the ontological paradox goes further. It doesn't just blur origins, it erases them completely, leaving behind a cosmic version of chicken or the egg. Consider the implications for history itself. What if some of humanity's greatest breakthroughs weren't invented but recovered? The Antikythera mechanism, an ancient Greek device often called the world's first computer, baffles historians with its advanced engineering. Could it be a relic from a future civilization, sent back in time only to inspire the very technology that eventually created it? Or take Leonardo da Vinci's sketches of helicopters and submarines, ideas centuries ahead of their time. Were they flashes of genius or echoes of knowledge yet to come? The paradox also raises eerie questions about free will. If a time traveler's actions in the past were always part of history, does that mean their choices are illusions? When Shakespeare puts quill to parchment, is he truly creating, or just transcribing a play that, in some sense, never had a first performance? Some philosophers argue this doesn't diminish creativity, it just redefines it. The artist isn't a puppet, they're a vital link in a chain that has no start or end, a collaborator across centuries with their own future and past selves. For physicists, the ontological paradox isn't just a mind-bending puzzle, it's a stress test for the laws of the universe. If time travel is possible, does reality allow objects or information to exist without origin? Or would the universe impose some quantum correction, like a cosmic backspace key, to prevent such loops from forming? Until we understand the deeper rules of space-time, these questions linger like shadows at the edge of science, both impossible and inevitable, depending on who you ask. Perhaps that's the paradox's greatest lesson. Some ideas feel timeless not because they're eternal, but because they're trapped in time, cycling endlessly between inspiration and discovery. The next time you encounter a piece of art or science that feels eerily ahead of its time, ask yourself, did someone create it, or did it simply always exist, waiting to be found again? What if every morning you woke up to the same day, trapped in an endless rerun of your own life, where nothing you did could break the cycle? The time loop prison isn't just a sci-fi trope. It's a chilling thought experiment that forces us to confront time's most suffocating possibility, a universe where escape is impossible and every action resets like a scratched record. Films like Groundhog Day and Edge of Tomorrow turn this nightmare into dark comedy and action, but peel back the Hollywood sheen and you'll find theories that make fiction look tame. Cosmologists have seriously debated whether our entire universe might be locked in a cosmic scale loop, destined to collapse and rebirth endlessly, a concept called the cyclic model. Imagine living the same century over and over, with no memory of the last iteration, every laugh, tear, and heartbeat preordained. The terror of small-scale loops cuts deeper. Picture realizing too late that your attempts to fix a mistake only cement it further. You save a loved one from a car crash, only to watch them slip and fall that night. You confess your heart out to someone, and no matter how they respond, time rewinds, erasing the moment like sand under a wave. Philosophers call this eternal recurrence, an idea Friedrich Nietzsche toyed with. What if you had to relive your life, identical in every detail, infinite times? The horror isn't just repetition, it's the erasure of progress, the futility of effort in a universe that refuses to learn. But what if the loop isn't punishment but a glitch? Some quantum physicists speculate time loops could form naturally in regions of extreme gravity, where space-time knots itself like a tangled shoelace. Fall into one and you might experience a slice of time on repeat, like a DVD skipping over the same 5-second clip. The twist, you wouldn't know it's happening. Your consciousness might reset with each cycle, leaving only déjà vu as a clue that today's conversation has happened word for word 1,000 times before. The cruelest version of this prison isn't physical, it's existential. In the Star Trek, The Next Generation episode Cause and Effect, the cruise ship explodes again and again, their memories wiped clean each time. Only Data, an android, senses the repetition, his subconscious smuggling clues through dreams. Real-world theories of temporal echoes suggest something similar, that traumatic or energy-rich events might imprint on space-time, replaying fragments like a cosmic recording. Ever walked into a room and felt an inexplicable dread? Some argue you're brushing against a loop, a moment of suffering trapped like a fly in amber. Yet there's a haunting beauty to these cycles. Buddhist teachings speak of samsara, the wheel of rebirth, where enlightenment comes only by breaking the pattern. Even modern psychology recognizes the loops we create ourselves: toxic relationships, self-sabotaging habits, emotional time machines we step into daily. Maybe the deepest fear isn't being trapped in time, but realizing too late that we've built the prison ourselves, one choice at a time. Whether through cosmic accident, quantum error, or some undiscovered law of reality, the time loop forces one question: if today repeated forever, would you change anything? Or would the universe, in its infinite indifference, keep hitting replay on a story you're powerless to edit? Einstein's theory of relativity gave us the cosmic speed limit: nothing can outpace light. But what if you didn't need to break the rules? What if you could cheat by bending the track instead? That's the audacious promise of the Alcubierre warp drive, a theoretical engine that wouldn't move a ship through space but would twist space-time itself, carrying you faster than light without ever accelerating locally. Imagine standing on a surfboard while the wave beneath you does all the work, except in this case, the wave is the fabric of reality, and your destination rushes toward you while you stay perfectly still. The concept, first proposed by physicist Miguel Alcubierre in 1994, relies on warping space-time in a very specific way. Picture a bubble forming around your ship, with space contracting violently in front of you and expanding behind you. Inside this bubble, you'd experience normal physics: no crushing g-forces, no time dilation, while the universe outside moves at impossible speeds. It's like rolling a marble across a stretched rubber sheet. If you scrunch the sheet ahead of the marble and smooth it out behind, the marble moves without technically traveling the distance. But here's where it gets wild, because the ship itself isn't moving through space. It's the space around it that's shifting. You'd sidestep relativity's nastiest side effects. No time dilation means astronauts could reach Alpha Centauri in weeks and return to an Earth that hasn't aged centuries without them. No grandfather paradoxes, no causality violations, just a smooth ride on the wrinkles of space-time. Of course, there's a catch. Building this cosmic shortcut requires exotic matter with negative energy density, a substance that defies everything we know about physics. Normal matter gravitationally attracts, but exotic matter would repel, creating the anti-gravity needed to stretch and squeeze space-time. The closest we've come is the Casimir effect, where quantum fluctuations generate tiny amounts of negative energy between closely spaced plates. To power an Alcubierre drive, you'd need oceans of this stuff, enough to wrap around a starship like a cosmic treadmill. Even if we solved the exotic matter problem, there's the issue of apocalyptic side effects. Calculations suggest the warp bubble's leading edge would concentrate enough energy to vaporize anything it touches, including your destination. Arrive at a planet, and you might unleash a gamma-ray burst powerful enough to sterilize it. Some models even predict that creating the bubble would require more energy than exists in the observable universe, turning the dream into a cosmic-scale battery problem. Yet for all its impracticalities, the Alcubierre drive isn't just sci-fi. NASA Eagleworks lab has experimented with miniature warp field interferometers, and theoretical refinements suggest ways to reduce the energy requirements. Maybe we'll never build a full-scale version, but the idea reshapes how we envision interstellar travel, not by fighting the universe's rules, but by rewriting the road beneath us. And that's the true genius of the concept. It reminds us that sometimes the fastest way forward is to bend the world instead of breaking it. Stephen Hawking, the legendary physicist who decoded black holes, once proposed a radical safety feature woven into the universe itself, a cosmic fail-safe against the chaos of time travel. His chronology protection conjecture suggests that the laws of physics might actively sabotage any attempt to violate causality, like a hidden referee blowing the whistle before paradoxes can unfold. Picture building a time machine only for it to malfunction at the critical moment, not by accident, but because reality itself refuses to let you break the rules. Hawking famously joked that the absence of tourists from the future is the best evidence time travel will never exist. But behind the humor lies a profound question. What if the universe has a built-in expiration date for paradoxes? At its core, this idea is about self-preservation. Causality, the principle that causes must precede effects, is the glue holding reality together. Mess with it, and the entire structure of physics could crumble. Hawking speculated that quantum mechanics might enforce chronology protection through tiny, unavoidable disruptions. Imagine trying to stabilize a wormhole for time travel, only for quantum fluctuations to generate an unstoppable feedback loop of energy, vaporizing the portal before it opens. It's like cosmic censorship. The universe steps in to blur the forbidden parts of the equation, ensuring no observer ever witnesses a contradiction. One dramatic example lies in the behavior of vacuum energy. Theoretical models show that as a time machine's mechanisms activate, the energy density in its core would spike toward infinity, creating a runaway effect similar to division by zero in a calculator, a crash so catastrophic it halts the process entirely. Even if you somehow survived the energy surge, general relativity suggests spacetime would warp into a singularity at the moment of paradox, like a computer blue screening to prevent corrupted data from spreading. But here's where it gets stranger. Some interpretations of quantum mechanics suggest chronology protection might not be a law, but an emergent property, a side effect of countless tiny interactions conspiring to keep history consistent. Think of it like a crowd unconsciously maintaining social distancing. No central enforcer is needed, just individual particles following local rules that collectively prevent timeline violations. This could explain why time appears to flow forward despite physics equations working just as well in reverse. The arrow of time isn't a fundamental law, it's the universe's immune system at work. Critics argue Hawking's conjecture is more philosophical than physical, an elegant assumption without definitive proof. After all, we've never observed a paradox to test whether nature intervenes. Yet supporters point to tantalizing clues, like the instability of wormholes under quantum scrutiny, or the way black holes seem to bleach information that could otherwise loop back destructively. Even if chronology protection isn't invincible, it might be statistically overwhelming, like a casino's edge ensuring the house always wins in the long run. The beauty of this idea is its humility. Instead of declaring time travel impossible, it acknowledges the universe's knack for self-correction. Perhaps causality isn't a fragile pane of glass, but a self-healing membrane, flexing under pressure but never tearing. For would-be time travelers, that's both a disappointment and a comfort. The past might be locked away not by our ignorance, but by the cosmos's quiet insistence on keeping the story straight. After all, if the universe has survived 14 billion years without unraveling, maybe it knows something we don't. What if the time travelers we imagine aren't rewriting history, just hopping to a better version of it? The multiverse rescue hypothesis flips the script on traditional time travel narratives by suggesting that messing with the past doesn't erase your original timeline. It just nudges you onto a parallel track where the disaster never happened. Think of it like swapping trains mid-journey. Your old reality chugs onward, scarred by tragedy, while you step into a world where the crisis was averted. No paradoxes, no erased ancestors, just a silent pivot to a universe where your intervention worked. This idea gains traction from the many worlds interpretation of quantum mechanics, where every decision spawns alternate realities. Under this model, a time traveler attempting to stop 9/11 wouldn't overwrite our timeline's horrors. They'd branch off into a new universe where the attacks were thwarted. The original world remains untouched, its pain unaltered, while the traveler and those they save live on in a fresh timeline. It's a grim but elegant solution to the grandfather paradox. You can't erase your own history, but you can abandon it for a better one. The implications are staggering. Historical mysteries might hide evidence of these invisible defections. Take the Philadelphia experiment urban legend, where a naval ship allegedly teleported in 1943, leaving crew members fused to bulkheads or vanishing entirely. Conspiracy theorists whisper that the disappeared didn't vanish. They slipped into adjacent timelines, casualties of a botched dimensional jump rather than a physics experiment. Similarly, reports of time slips, like the infamous Montauk Project claims, could reflect accidental multiverse shifts where subjects crossed into realities with subtly altered histories. Critics argue this hypothesis lets time travelers off the hook morally. If your original world still suffers, are you truly saving anyone or just curating your own survivor's guilt? Supporters counter that even branching realities have value. In one universe, a plague wipes out millions. In another, your actions grant countless beings a future. The math of existence tips toward more life, more joy, even if some threads remain dark. Here's where it gets ethically thorny. If multiverse rescues are possible, should travelers prioritize branching over fixing? And how would we even know if our world is the original or a fork created by some future intervener? The hypothesis forces us to confront a brutal truth. Salvation might not mean rewriting the past, but accepting that some wounds are permanent and choosing to build new worlds beside them. The most haunting question isn't whether this could happen, but whether it already has. If countless alternate realities exist, how many bear the fingerprints of unseen meddlers? Our universe's narrow escape from nuclear war, the inexplicable survival of key figures, could these be the work of refugees from darker timelines, forever weaving new futures just one dimension over? The multiverse rescue hypothesis doesn't just redefine time travel, it suggests we might already be living in someone else's second chance. The most unsettling version of survival isn't cheating death, it's outrunning it forever without realizing you're playing the game. Quantum immortality takes Schrödinger's cat to its logical extreme. If every quantum event spawns alternate realities, then there's always a timeline where you survive against impossible odds. Now imagine coupling this with time travel not as a journey through history, but as an unconscious slide into the realities where you didn't fail. Picture a traveler attempting to leap back to ancient Rome, only for their machine to malfunction catastrophically. In most branches of the multiverse, they're vaporized or lost in the void. But in one vanishingly slim thread, some freak quantum fluctuation keeps the machine intact just long enough to complete the jump. From their perspective, the trip worked flawlessly. They'll never know about the infinite graves holding their other selves. This isn't just speculation, it's a byproduct of how quantum mechanics might interact with consciousness. In the many worlds interpretation, every decision point fractures reality, but your awareness only follows the path where you continue to exist. Apply that to time travel, and every risky jump becomes a dice roll with unseen consequences. A traveler testing a prototype machine might experience a string of miraculous near-misses, circuit failures that somehow self-repair, fuel leaks that inexplicably seal. They'd chalk it up to luck, never realizing that in most branches they died screaming. Only the threads where they survive remain observable to them, stitching together a narrative of improbable success. The eerie part, this could already be happening. Ever narrowly avoided a car crash or brushed off a close call with death? Under quantum immortality, those aren't just lucky breaks. They're proof you're inhabiting one of the few timelines where you persisted. For time travelers, the stakes are infinitely higher. Attempt to witness the Cretaceous period, and a million versions of you are torn apart by dinosaurs or suffocated in an oxygen-poor atmosphere. But the version that returns, that's the one where every possible break went their way, from avoiding predators to stumbling upon a pocket of breathable air. The traveler remembers only the triumph, never the countless failures they didn't live to recall. Critics argue this reduces existence to a cosmic casino where the house always wins. Your consciousness just keeps cashing tickets from the winning slots. Yet the theory holds a perverse comfort. Failure might be far more common than we perceive, but our awareness is wired to ignore it. Like a film editor slicing out every flub take, we experience only the final cut where things work. For would-be time travelers, that's both a warning and a revelation. Your journal might record a flawless voyage, while the multiverse burns with the evidence of all the ways it could have gone wrong. The next time you marvel at history's narrow escapes, a leader surviving assassination, a civilization dodging collapse, ask yourself, how many other versions of this moment ended in silence? And are we the lucky ones, or just the ones who got to keep counting? What if the arrow of time isn't an arrow at all, but a two-way street we're only seeing half of? The time-symmetric universe theory shatters our most basic assumption, that time moves inexorably forward. At the quantum level, the laws of physics don't actually care about direction. Equations for particle interactions work just as well whether time flows toward the future or the past. The only reason we perceive a forward is thanks to entropy, the universe's tendency toward disorder. Think of it like a shattered wine glass. You'd never see the shards spontaneously reassemble, not because physics forbids it, but because the odds are astronomically stacked against it. Yet fundamentally, every fragment could reverse its path. It just never does in our observable reality. This symmetry hides in plain sight. Take a film of two billiard balls colliding, played forward. They strike and rebound. Played backward, the motion looks identical. Now imagine that logic applied to everything. Electrons, photons, even entire molecules dance to time-neutral rules. The catch, complexity scrambles the symmetry. While a single particle might not know past from future, a cup of coffee cooling on your desk absolutely does. The difference lies in scale. The more moving parts, the more entropy stamps a direction onto time's flow. That's why we remember yesterday but not tomorrow, not because the future is inaccessible, but because our consciousness is wired to ride the entropy wave in one direction. Some interpretations push this further. The transactional interpretation of quantum mechanics suggests particles send signals both forward and backward in time, with reality emerging from a handshake between past and future. Picture a photon emitted by a star. In this view, it's not just radiating outward, it's also receiving influence from the atoms that will eventually absorb it, like a cosmic game of catch where the ball is thrown and caught simultaneously from both ends. If true, time's asymmetry isn't a law, it's a quirk of perspective, a shadow cast by our limited perception. Here's where it gets mind-bending. If time is fundamentally symmetric, could there be regions of the universe where entropy flows the other way, where cups of coffee heat themselves and people age backward? Physicists like Sean Carroll have argued that a truly infinite cosmos might contain anti-entropic pockets, entire galaxies where time appears reversed to us. Observers there would swear their reality moves forward, branding us as the backward ones. It's a cosmic mirror where both reflections are equally valid, we just happen to live on one side. The implications ripple into time travel. If the universe doesn't inherently distinguish past from future, traversing time might not require bending physics, just flipping the script. A traveler moving backward wouldn't violate causality. They'd simply be dancing to entropy's rhythm in reverse. Of course, they'd still face the same problem as a rewinding VHS tape. Everyone else is playing forward, making interaction nearly impossible. You can't shake hands with someone moving toward your past while you're headed toward their future. You'd phase through each other like ghosts in opposite flowing streams. Yet the theory offers a radical comfort. Time's flow isn't absolute. It's a narrative we stitch together from chaos, a story we tell ourselves to make sense of the universe's indifference. Whether through quantum handshakes or mirrored entropy zones, the time-symmetric universe whispers that the past and future might be closer than we think, two sides of a coin we've only ever seen tails up. What if the future isn't just unwritten but actively editing the past? Retrocausality flips everything we think we know about cause and effect on its head, suggesting that particles at the quantum level can be influenced by events that haven't happened yet. The most jaw-dropping evidence comes from the delayed choice quantum eraser experiment, a setup so bizarre it feels like the universe playing a prank on physicists. Here's how it works. A photon is fired at a screen through a barrier with two slits, creating an interference pattern that suggests the photon behaves like a wave, passing through both slits simultaneously. But if you place detectors at the slits to observe which path the photon takes, the interference pattern vanishes. The photon chooses to act like a particle. So far, standard quantum weirdness, but here's the twist. What if you wait until after the photon has already passed through the slits, but before it hits the final screen, to decide whether or not to look at its path? Astonishingly, the photon's behavior changes retroactively, as if your future decision reaches back in time to dictate whether it acted as a wave or a particle in the past. This isn't just theoretical sleight of hand. In labs around the world, variations of this experiment have been conducted with atoms, electrons, even molecules. Each time, the results point to the same unnerving conclusion. Quantum systems don't just respond to present conditions, they're entangled with future measurements in ways that defy classical logic. Imagine mailing a letter and then, days later, choosing whether to send it express or standard delivery, somehow altering how quickly it traveled in retrospect. That's the level of temporal flexibility we're talking about at the quantum scale. Critics argue this doesn't truly violate causality, since no usable information is sent backward, just probabilities adjusting behind the scenes. But supporters counter that it reveals a deeper truth. Time might not be the rigid, one-way street we perceive. Think of it like a cosmic game of telephone, where the future whispers hints to the past, shaping events without ever fully breaking the rules. The delayed choice eraser suggests that quantum systems don't collapse into definite states until the entire experimental setup, including future choices, is taken into account. It's as if reality waits for all the receipts before balancing its books. The implications ripple far beyond the lab. If particles can be swayed by future observations, could larger systems, even consciousness itself, be entangled with events yet to come? Some interpretations of quantum mechanics propose that retrocausality might explain precognitive dreams or déjà vu flashes where the brain momentarily syncs with a timeline where cause and effect aren't strictly linear. Even more radically, this could hint at a universe where the distinction between past and future is an illusion, a side effect of our limited perception. Perhaps the most humbling takeaway is how retrocausality forces us to rethink agency. If a particle's past state depends on future measurements, then now might just be a negotiation between what was and what will be, a handshake across time we're only beginning to decode. The next time you agonize over a decision, remember, at some level, the universe might already know how it ends, quietly adjusting the threads of reality to make sure the story stays consistent. Whether that's comforting or terrifying depends on how tightly you're holding onto the illusion of control. What if the entire history of the universe, every star, every civilization, every moment you've ever lived, was just lines of code in an unfathomably advanced simulation? This is the core premise of the simulation argument, a theory that's gained startling traction among philosophers and tech billionaires alike. And if it's true, then time travel might not be a feat of physics, but something far stranger, a backdoor command used by the architects of our reality. Think of it like hitting Ctrl+Z on cosmic scale, not bending space-time, but editing the save file of existence itself. The idea takes root in simple logic. If civilizations more advanced than ours inevitably create hyper-realistic simulations, whether for entertainment, research, or preservation, then the odds say we're statistically more likely to be in one of those simulations than in the original universe. Now imagine those creators need to troubleshoot their creation. A glitch causes World War III to erupt in 2040. They'd roll back the clock, tweak a few variables, and rerun the scenario until it stabilizes. To us, that might look like history mysteriously shifting planes that vanished suddenly landing safely, political assassinations that never happened, or Mandela effects where millions swear events unfolded differently. This reframes time travel not as a violation of natural laws, but as a feature built into the system. Ever played a video game with a rewind function? Games like Prince of Persia or Braid let players undo mistakes by scrubbing time backward, observing how tiny changes ripple into new outcomes. If we're living in a simulation, our universe could have similar developer tools accessed not by us, but by the entities running the program. Historical anomalies like the Tunguska event or the abrupt cancellation of the Philadelphia experiment might be patches applied by unseen coders, fixing bugs before they crash the simulation. The eerie part, this could explain why time travel paradoxes seem impossible. In a simulated universe, causality is just a rule set by the program. If a time traveler creates a contradiction, the system could auto-resolve it by spawning a parallel instance or rewriting the affected parameters. The grandfather paradox wouldn't crash reality. It would trigger a subroutine that branches timelines or tweaks memories to preserve consistency. Even déjà vu could be a glitch, a momentary awareness of the save points where the simulation was rolled back. But who's at the controls? Some theories suggest our simulators might be future versions of humanity, running ancestor simulations to study their origins. Others propose transcendent AI or alien civilizations treating our universe like a cosmic sim city. Either way, their motives would dictate how time travel manifests. Research simulations might allow limited rewinds to test historical variables, while entertainment sims could feature scripted time loops for narrative drama. The darkest version, we're prisoners in a recursive sim, doomed to relive the same century endlessly while observers study our reactions. The simulation argument doesn't just demote time travel from physics to programming, it raises existential questions about agency. If our past can be debugged by higher operators, are any of our choices truly ours? Or are we non-player characters in a universe where history is just the latest patch notes? For now, it remains a thought experiment tinged with both wonder and dread. The possibility that our most audacious dreams of time manipulation might just be someone else's undo button. What if time travelers aren't just visitors to the past, but ghosts in the machine, gliding through history untouched by the chaos they create? The idea of time travelers' immunity suggests that paradoxes might not just be avoided. They could be physically impossible, thanks to quantum mechanics or hidden laws shielding reality from unraveling. Imagine stepping back to the 1920s and accidentally leaving your smartphone on a park bench. Instead of altering the course of technology forever, the device might malfunction, get lost in the mud, or simply vanish, not by chance, but because the universe enforces a kind of temporal hygiene, scrubbing away inconsistencies before they can metastasize. This theory borrows from quantum mechanics' weirdest loopholes. At the subatomic level, particles exist in probabilities, not certainties. Apply that fuzziness to time travel, and your actions might not have fixed outcomes. Try to assassinate a historical figure, and quantum fluctuations could conspire to make you miss, not because of fate, but because every possible interaction splinters into parallel realities, leaving only the self-consistent ones observable. It's like rolling a million-sided die where every result that would break causality simply doesn't count. Physicists call this post-selection, a cosmic filter ensuring only non-paradoxical timelines survive. You're not changing history, you're auditioning for versions of it where your presence doesn't torch the script. But what if the protection isn't just quantum luck, but something more deliberate? Some models suggest time travelers might emit a kind of paradox radiation, an unseen force field of negative energy that repels contradictions. Picture walking through a crowd in ancient Rome. People unconsciously step aside. Objects slip from your grasp before you can leave an anachronism behind, and your words fade into the noise before they can alter major events. Like a hand brushing against wet paint but coming away clean, your influence is somehow always superficial. This wouldn't be magic. It could be a natural consequence of closed time-like curves, where space-time loops force events into alignment like train tracks bending back to meet themselves. The darkest version of this immunity isn't about protection, it's about erasure. If a traveler's actions threaten to destabilize history, the universe might correct not by stopping them, but by removing their impact retroactively. Save a scientist from a fatal accident, and they might die days later in a freak lab explosion. A statistical anomaly so precise it feels targeted. This temporal homeostasis would treat paradoxes like infections, with reality deploying invisible antibodies to neutralize threats. The traveler, unaware of the adjustments, would swear their efforts failed, never realizing the universe edited their attempts out of existence. Yet there's a haunting beauty to this idea. If immunity exists, it might explain why history feels so stubborn. Revolutionary ideas often emerge simultaneously across cultures. Suppressed inventions resurface in new forms. Like water finding cracks in stone, progress might be less about individual genius and more about the universe permitting certain breakthroughs only when the timeline is ready. Time travelers, no matter how well-intentioned, could be just another force the cosmos has learned to absorb, less architects of change than pebbles tossed into a self-healing stream. The ultimate irony: if immunity is real, we'd never know. Every failed time travel experiment, every vanished artifact or historical near miss, might not be proof it's impossible, just evidence the universe is better at cleaning up than we are at leaving traces. So the next time you read about an object found where it shouldn't be, or a prophecy that uncannily came true, ask yourself, was that a glitch in the matrix or the one clue the system missed? Imagine all of time laid out like a vast, unchanging landscape, every moment from the Big Bang to the heat death of the universe frozen in place, as real and solid as the words on this page. This is the block universe theory, the spine of eternalism, where past, present, and future don't flow but simply are. Think of it like a DVD. The scenes aren't being created as you watch, they're all already there. Your consciousness is just the laser moving through the disk, giving you the illusion of a now. Eternalism isn't some fringe idea, it's the child of Einstein's relativity, where space-time is a four-dimensional fabric. Gravity doesn't just bend space, it warps time too, meaning now is relative. Two events simultaneous for you might be years apart for someone moving at light speed. If time can stretch like taffy, then privileging one slice as real starts to feel arbitrary. The dinosaurs aren't gone, they're just over there in the space-time block, as fixed as ancient Rome on a world map. But then there's presentism, the gut-feeling counterargument. Only this breath, this heartbeat, exists. The past is gone like a blown-out candle, the future is unwritten. Presentism aligns with our raw experience. You can't revisit yesterday's sunrise or RSVP to next century's parties, yet it clashes brutally with relativity. If now is universal, how do you reconcile the fact that astronauts on the ISS experience time slightly slower than Earth-bound observers, whose present wins? The tension between these views isn't just academic, it reshapes how we imagine time travel. Eternalism suggests hopping to the past is no weirder than flying to Paris. You're just navigating the block. Presentism, though, makes time travel a metaphysical nightmare. If the past is truly erased, where would you even go? Philosophers like J.M. McTaggart argued eternalism kills free will. If the future's already out there, our choice is illusions. But others counter that decisions still matter, they're just part of the block, like brushstrokes in a finished painting. Meanwhile, presentism's fragility unnerves physicists. If only the present exists, why do quantum particles seem to remember their entangled partners' states across time? Perhaps the starkest difference is emotional. Eternalism offers cold comfort. Loved ones lost aren't gone. They're eternally preserved in their slice of space-time. Presentism, though, mirrors our grief. Loss feels absolute because the past is. Neither view is provable yet, but their debate forces us to ask, is time a river we float on, or a frozen sea we're carving paths through? The answer might not just define reality. It could rewrite what it means to be human in a universe where now is either everything or nothing special at all. Dark matter, the invisible glue holding galaxies together, might hide more than just missing mass. Some daring physicists speculate that these mysterious particles could be nature's own time machines, weaving hidden tunnels through space-time where the usual rules break down. Picture an iceberg. We only see the tiny fraction of matter that interacts with light, while beneath the cosmic surface, dark matter's unseen structures could form labyrinthine networks. If just 1% of these structures warp space-time in the right way, they might stitch together moments normally separated by millennia, no flux capacitor required. The math behind this idea stretches Einstein's equations to their limits. Dark matter's gravitational influence is undeniable. It bends light, sculpts galactic orbits, and outweighs visible matter 5-to-1. But what if its density isn't uniform? Certain models suggest ultra-dense knots of dark matter could create micro-black holes or cosmic strings, objects so massive they twist space-time into loops. Unlike classic wormholes, which require exotic matter to stay open, these dark vortices might stabilize naturally, fed by the very particles we can't detect. Imagine a hidden whirlpool in the ocean of space-time. Swim into the current, and you might emerge in another era. The most tantalizing clue comes from gamma-ray bursts, blazing cosmic explosions that sometimes arrive with inexplicable time delays. While mainstream science blames interstellar scattering, a fringe theory proposes these lags are evidence of dark matter time lenses. Photons skimming the edge of a dark vortex could get temporally displaced, like cars exiting a highway at different speeds. If true, the universe might be peppered with natural time warps, their signatures buried in data we've already collected. Critics argue this crosses into science fiction, but history's full of impossible ideas later proven true. Black holes were once laughed at as mathematical quirks. Now we photograph their shadows. The real hurdle is testability. How do you detect a tunnel made of invisible stuff? Some propose looking for echoes in particle colliders. If dark matter interactions briefly open time loops, certain collisions might produce particles with impossible energies or decay patterns. Others suggest studying ancient starlight for distortions that resemble time-lensed images. The darkest twist, these portals might self-censor. Just as black holes hide their interiors behind event horizons, dark matter time tunnels could erase evidence of their own existence. A traveler stepping through might find their arrival point shifted to ensure consistency, no paradoxes, just subtle edits to history's script. It's a haunting thought. The cosmos could be riddled with temporal shortcuts, their entrances camouflaged as cosmic noise, waiting for someone or something to learn how to read the map. What if the most powerful time machine isn't a device but your own mind? The consciousness time jump theory suggests that human awareness might be capable of something far stranger than physical time travel, slipping between alternate realities or historical moments through sheer mental focus. Think of those eerie stories where survivors of near-death experiences swear they lived entire lifetimes in other worlds, only to snap back to their bodies with inexplicable memories. Or meditators who claim to access past lives with such vivid detail they can describe ancient streets they've never visited. These aren't just hallucinations. Some researchers believe they could be glimpses of consciousness untethered from linear time. At the heart of this idea is a radical reimagining of what consciousness is. Traditional physics treats time as a dimension woven into space-time, but certain interpretations of quantum mechanics propose that observation itself might shape reality. The von Neumann-Wigner interpretation goes a step further, suggesting consciousness could be fundamental like space or gravity rather than just a byproduct of brain activity. If that's true, then focused mental states might interact with time's fabric in ways we're only beginning to understand. Picture a deep-sea diver adjusting their buoyancy to drift between ocean layers. Advanced meditators could be tuning their awareness to float into adjacent timelines or eras. Near-death experiences offer some of the most chilling anecdotal evidence. Take the case of a cardiac arrest patient who, while clinically dead, recalled watching surgeons from above and later described precise details of instruments used and conversations held despite having no medical training. Even stranger are accounts like Pam Reynolds, who underwent brain surgery with her body cooled to near freezing, her EEG flatlined. Yet she reported floating out of her body, observing the bone saw's unique shape, and overhearing a nurse's comment about her femoral artery, all later verified by the surgical team. If consciousness can detach like this, could it also slip into other moments entirely? Then there's the phenomenon of quantum mysticism in meditation traditions. Tibetan monks speaking of rainbow body attainment, where the physical form dissolves into light, echo eerily with quantum theories of matter as condensed energy. Yogis who describe accessing the Akashic records, a supposed cosmic library of all events past and future, might be tapping into what physicists call the block universe, where every moment exists simultaneously. Even modern biohackers experiment with binaural beats and sensory deprivation to induce states where time perception distorts radically, hours feeling like minutes or vice versa. Skeptics dismiss these claims as brain glitches, temporal lobe seizures, or oxygen deprivation spinning elaborate hallucinations. But proponents argue the consistency across cultures and eras is telling. From shamanic journeying to modern lucid dreaming techniques, the same themes emerge: time as a malleable construct, consciousness as a navigator. Some theorize that near-death states or deep meditation might briefly unlock quantum processes in the brain, allowing microtubules, tiny structures in neurons, to interact with space-time at a fundamental level. It's as if the brain isn't just a computer, but a receiver capable of tuning into different channels of time. The most tantalizing possibility: these shifts might happen constantly without our awareness. Ever had a gut feeling that saved you from disaster, or déjà vu so strong it felt like memory? Under this theory, those could be micro jumps, your consciousness brushing against a timeline where events played out differently. Even the Mandela Effect might be collective evidence of subtle timeline slips, with groups of people remembering versions of history that no longer exist. Whether these experiences are neurological quirks or genuine leaps through time's architecture, they force a humbling question. If consciousness can bend time, how much of our perceived reality is truly fixed? The answer might lie not in machines or wormholes, but in the uncharted depths of the human mind where past, present, and future could be waiting, not as destinations but as choices. Imagine harnessing the entire energy output of a star, not just collecting sunlight with solar panels, but wrapping the sun itself in a colossal megastructure designed to bottle every photon. This is the Dyson sphere, the ultimate power plant for a civilization that's outgrown planets. But what if this astronomical engineering feat could do more than just generate energy? What if it could bend time itself? Enter one of the most audacious theories in physics, a Dyson sphere repurposed as a cosmic-scale time machine, where the very fabric of space-time becomes a tool for temporal navigation. The concept starts with scale. A type Roman II civilization, one capable of building a Dyson sphere, would command energy on a level we can barely fathom. Envision a network of orbiting platforms or a solid shell encasing their star, capturing its full radiant power. Now take that raw energy and focus it. Einstein's equations tell us that mass and energy warp spacetime, creating gravity. A Dyson sphere's civilization wouldn't just use energy, they could weaponize it, twisting local spacetime into knots through sheer gravitational force. The sphere's structure could be engineered to create rotating rings of unimaginable density, essentially forming a Kerr black hole's ergosphere, a region where spacetime itself is dragged into rotation. Step inside this engineered vortex, and you'd find yourself in a place where time slows relative to the outside universe, or even loops back on itself. Here's where it gets wild. By carefully controlling the sphere's rotation and energy distribution, such a civilization might create time corridors, paths where the distinction between past and future blurs. Need to send a probe backward a millennium, align the energy beams just right, and the probe's trajectory could emerge at an earlier point in the star's timeline. It's like throwing a ball into a whirlpool and watching it reappear upstream. The Dyson sphere wouldn't just be a power source, it would be a temporal lighthouse, its gravitational lens bending not just light but causality. But why would a civilization build this? Survival, for one. A star's lifespan is finite, but mastery over time could offer escape routes. Imagine detecting an incoming gamma ray burst destined to sterilize your system in 10,000 years. With a Dyson time machine, you could shunt key resources, or your entire civilization, into an engineered past or a slower-moving timeline, effectively dodging the catastrophe. Or consider knowledge preservation. Libraries encoded in neutronium, launched into time loops where they're accessible to future iterations of your society across millennia. The catch: stability. A Dyson sphere time machine would teeter on the edge of cosmic disaster. Misalign the energy flows, and you might collapse the structure into a singularity or rip spacetime seams wide enough to erase your star from history. Some models even suggest that the energy required to sustain time loops could accelerate the star's burnout, trading temporal control for the very resource powering it. Yet the tantalizing possibility remains. If advanced civilizations exist, their greatest monuments might not be city-sized sculptures or radio beacons. They could be stars wrapped in silent, spinning labyrinths, humming with the power to rewrite time itself. And if we ever spot a star flickering in ways that defy physics, it might not be a natural phenomenon. It could be the signature of engineers who have turned their sun into more than a power source, a clock that ticks backward when they need it to. From closed time-like curves weaving through black holes to the Mandela Effect hinting at rewritten histories, we've journeyed through 30 of the most astonishing theories about time travel, each one stretching our understanding of reality to the breaking point. Think about the Bootstrap Paradox, where objects and ideas exist without origin, caught in an endless loop of their own creation. or the chilling predestination paradox, where every attempt to change history only locks it more firmly into place. And who could forget quantum immortality, the idea that your consciousness might be surfing an endless wave of survival, oblivious to the countless timelines where you met a grim end. These aren't just thought experiments, they're windows into how the universe might actually operate under the hood, where time isn't a straight line but a tangled web of possibilities. Some theories flirt tantalizingly with plausibility. Einstein's relativity already proves time dilation is real. Astronauts on the ISS age microseconds slower than Earth-bound humans. Could closed time-like curves or Alcubierre's warp drive be the next frontier? Even the many worlds interpretation, once dismissed as sci-fi, now has serious backing from quantum physicists. Then there's the eerie consistency of the Mandela Effect. Could it really be evidence of timeline shifts or just quirks of human memory? The line between science and speculation has never been thinner. But here's the real question: which theory left you reeling? Was it the holographic principle, suggesting our 3D reality is just a projection from a 2D boundary where past and future coexist? Or the idea that dark matter, stuff we can't even see, might be riddled with natural time tunnels? Maybe it's the simulation argument, where time travel is just a debug command in someone else's cosmic code. Whatever it is, let us know in the comments. We're obsessed with these mysteries too. If your brain's buzzing with more questions than answers, you're not alone. Time travel isn't just about machines and paradoxes, it's about probing the deepest nature of existence itself. So hit that like button if you're ready to dive deeper, and subscribe for more mind-bending journeys into the unknown. The universe is stranger than we can imagine, and together we're just scratching the surface. Until next time, keep questioning, keep wondering, and who knows? Maybe one day we'll meet in the past or the future.